one more day on 7-2. So we finish up 7-2 today with the compound interest formula. And it's going to feel a lot like the stinky green shampoo formula. It just has a little bit more going on with it. Instead of the APERT that we were using for continuously compounded, we got a few more blanks to fill in with this one. But this is the last piece to 7-1 and 7-2. And then tomorrow we will do the practice test and have a review assignment. And on Thursday you'll take the test. Friday there will be a video lesson. And that video lesson will be the start of our MCA ACT prep on Friday. So, busy week. Compound interest formulas. This is actually the formula that's super close to what Euler was using to try to develop that always charging people interest piece. And compound interest formulas are typically used when we're not just compounding it every year. So, we have a formula for that one. If it says annually, we can still use our little growth formula from before. So we don't have to use this one when it says annually. Annually, you can just go ahead and use our nice little easy growth formula. You could also use this big monster formula, because as we're going to see through here, n is the number of times that you're going to compound this each year, so you could just make that a 1, and then you'll get that formula anyway. But let's talk about what this big monster has. So A, final amount, equals P, principal, times the quantity, 1 plus R, interest rate is a decimal, divided by n, number of times each year that this is compounded. And notice that n gets 2 spots up here. That's one of the things that students who have their first time ever working with this formula forget, that the n is actually in 2 spots. They talk themselves out of that because they think, well, I can't go in both places. Yes, it does in this formula. And then T is the number of years. So, capital P, principal amount. How much did you put into the bank? That's what that capital P is for. We should be used to this interest rate of our business by now. That's your annual rate of interest as a decimal. Whenever you take a percentage and you put it into a math formula, you have to move the decimal 2 places. Then we have the number of years, which is a little t. Capital A, how much money are you going to get? How much will be in that savings account? Or on the flip side, the banker is saying, you owe me this much for your loan. And then this is the new one where we have to think about it a little bit, and that's n for the number of times the interest is compounded per year. Now, if they say annually, n is 1. Easy to do. But for most banks, savings accounts, they're going to be quarterly. And there are 4 quarters in a year, so n would be 4. Now, unfortunately, credit cards, if your folks have any and they've sat down to talk to you about that, credit cards actually accumulate interest monthly, but in some cases daily. And so, they've got the advantage over us with the savings accounts that are only going to compound quarterly. So here's a list of words you would commonly hear the bank say in your statements. Annually, n is 1. Semi-annually. Now, you may not have heard that from the bank. You may have seen, like a Macy's flyer come in and it said semi-annual home sale. That means twice a year. So semi-annually is twice a year. Quarterly, 4 times a year. Like I said, that's the big one because most savings accounts will do that. Monthly, we're going to use a 12. There's 12 months in the year. And if it's daily, then we're going to use 365. So that n, you have to think about it. What did they say? What was the word they used? And most banks do say semi-annually, but a few of them will still say biannually. So I'll have you write that one down next to semi-annually. But we all know bicycle has two wheels. That's how it works. So there it is. Well, that's all we get. We get a new formula, and we get what the little letters stand for, and already they're throwing a problem at us because they're formula problems. That's what they are. This one says, suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? So the first thing I was looking for was this. Everything we did yesterday, we had to see compounded continuously or continuously compounded, and that's how we knew to use the stinky green shampoo formula. That's not this one. That does not say continuously compounded. It says annual interest. So I have a choice, because annual is just once a year. I could just use my tiny little growth formula, or I could use this and put ones in for n. Totally up to you which one we do today. Now, we're definitely going to have to use this formula in some of the other cases. So would you use the black one or the red one? Which one do you want to go with? Do the red while we can? Sure. Why not? So there's our little growth formula. We'll let the formula lead us to what we need. Well, it says how much is in the account after 5 years. That's A of t. That's what we're going to find. We need to know how much they put in to start with. How much was that? 500 smeckers. 1 plus, let's turn that interest rate into a decimal. What would that be? 0.035. And did they tell us how many years? They said 5. And we worked with this formula before. You know, it's a little easier to punch in if you just do the dollar plus 0.035 yourself. But it really is just calculator. So if you have your own graphing calculator, grab that out. If you've got a phone that you have calculator capabilities on there, you might want to grab that. You know what? Let's not do that, because you can't use your phone on the test. Chromebook, TI-84 Rapid Identity. Get that out of there, because we're going to be using those calculators a lot today. This one we could probably punch in on your phone and not have any problems, but some of them we're going to do today, it's pretty involved. So we need 500, 1.035 for 5 years. $593.84. Because it's your money, and you want to pay attention to that. You want to make sure you're getting what you're supposed to get. So again, the reason we could pick the shorter formula with this one is because it said annual, which is just once a year. This one says an amount of $1,500 is deposited into a bank paying annual interest rate of 4.3%, but oh, look what that's followed up by. Compounded quarterly. What is the balance after 6 years? Can't use the short formula this time. This one's compounded quarterly. So let's go grab that big monster. P times, and then we had 1 plus r over n to the nt. And every time we do these, you're going to see me write the formulas down. Because once you have the right formula, then just let the formula tell you what it needs. I mean, remember what the letters say. What's the balance after 6 years? So we're trying to find the big capital A. Did they tell us how much money they put in the bank? $1,500. 1 plus, what's our interest rate as a decimal? 0.043. And the reason we had to use this formula was because it's compounded how many times a year? 4 quarterly. And we have to remember to put that in 2 spots. And then did they say how many years? 6. All right, so what math should I do on this cedar home before I punch it in? The 4 times 6. I mean, really, the rest of this we're going to have to punch in. And I want to make sure that everybody knows that you really should punch it in according to the order of operations so that your calculator doesn't have to figure out what you want it to do. And the order of operations says we start with parentheses first. So I look at this and I think, well, then I probably better punch in the fraction first, because 0.043 divided by 4, I better put that in parentheses. Then I'll add the 1. Then I'll raise the whole thing to the 24th power, and I'll multiply it by 1,500. And then I'm sure I have the right answer. I'm not turning over the process to the calculator. I'm saying, calculator, I am in charge. Do what I'm telling you to do. So again, I start with parentheses 0.043 divided by 4. Then I'm going to add 1 and get the answer. Now I'm going to raise that to the 24th power and finally multiply that by 1,500. Oh, I didn't hit answer. Let me try again. 0.043 divided by 4 plus 1 to the 24th. And then times 1,500. There we go. $1,938.84. There it is. So like I said, some people like to do the whole punch it in at one time. If you do that, you're going to want an extra set of parentheses in here so you can just punch it in from left to right to tell the calculator 0.043 divided by 4 is a fraction. Like I said, I prefer to do this. Punch this in as step 1, this in as step 2, this is step 3, and multiply for step 4. And then I know what's going in there right. I'm not trusting the calculator to follow the order of operations. Alrighty, that's definitely not enough practice. Since you were such a sweet baby, your wealthy grandmother decides to start a college fund for you. She invests her life savings of, well, now she doesn't sound so wealthy anymore. When we originally did this, we put $20,000 in here, and that sounded like a lot of money. That'll get you about 2/3 of your way through the first year of college now. $20,000, and she managed to find a bank that would give her 3% interest. And, of course, they compound it quarterly, as most banks do. How much will be in the account when you start college 18 years later? Well, at least it's going to grow. I mean, that's a good sign. So with this one, can I use our little shortened red formula, or do I have to use the Monster Black formula? Monster Black. It's quarterly. What was the principal? What did Grandma put in the bank? Yep. Sure you get all your zeros. Interest rate is a decimal? Uh-huh. And what are we using for N? 4 for quarterly. Make sure you put that in both spots. And how many years was that going to be in there? 18. So again, I'd probably do the 18 times 4 in my noggin beforehand. Wouldn't have to. You know, you could punch it in and then say raise to the 4 times 18 power if you want to. And then we'd be very careful about punching this in. Parentheses, 0.03 divided by 4 plus 1 to the, and here's the part where I said if you just wanted to leave it and punch in 4 times 18 right here, you could do that. The calculator will do that for you. and then multiply that by 20 grand. Now the first year of college is probably paid for. $34,251.05. And then the time it took me to move that back, I have lost some numbers. 251.05. There we go. But at the time, 20 years ago, $20,000 might not have sounded too bad, you know, for paying for college. Problem 4, using exponential growth. That's what a bank account is. You know, it should be going up if your savings account. It should increase. Suppose you invest $1,000 in a savings account that pays 5% annual interest. If you make no additional deposits or withdrawals, how many years will it take for the account to grow to at least $1,500? Well, I don't know. Let's see. It says we can just use our growth model for this one. So let's go back to this. Now, they didn't have to tell us that, because inside here we don't see anything about semi-annually, quarterly, daily, monthly. We don't see any of that in here. It mentions that this has annual interest, so that's once a year. Now, we want to know if we put $1,000 in, when will we get at least $1,500? So this time we do know what we're supposed to get for an answer. It's supposed to be 1,500. So we've got 1 plus, what's our interest rate as a decimal? 0.05. And we don't know T, but we do know a dollar plus a nickel is going to be $1.05. And we're in the same situation we were in yesterday. We can't solve this without knowing logarithms. So we're going to turn this over to Blinky and let Blinky help us out with this. This will be y sub 1, y sub 2, and we'll check and see when they hit each other. So let me move this down so I can still see it and punch it in. Y equals 1,000 parentheses 1.05 to the x, because the calculator couldn't care less what variable you use. Enter 1,500. All right, so here's the thinking part, and this is usually when I'm wandering around, people are asking about this. We've got to go to the window. We have $1,000 in the account now, and we want to know how long it's going to take it to get to 1,500 if it's 5% interest. What do you think? Give me some numbers here. Number of years. 0 to 10 years? 0 to 20 years? 0 to 30? Anybody else out there have an idea? Well, let's try 0 to 10. Let's see. We know we have to be able to see 1,500. Well, right now, my calculator is set for a max of 3. That's not high enough. I'll go with 2,000. And we're hoping we can see it. Well, there it is. So it is. It's within 10 years that we're going to get $1,500. Now, how do we call it, Blinky, again? Second trace. We're doing number 5. And since those are the only graphs I have in there, I can hit enter 3 times. And Blinky says it's going to be about 8.3 years for that money to be $1,500. But here's what we know. If you go in after 8.3 years, are they going to give you $1,500? No, because the bank, they all say you have to wait until the end of the year to get your money. So reality is it's going to be 9 years for you to get that money. So it's another good to know. You know, the math works one way, but The banks work a different way, and we have to realize we don't want to walk in there and make a big stink because they're not giving us their money when right in the contract it says you can't get it until the end of the year. So what we just saw is this. When we graph these on the graphing calculator, they graph as lines, as curves, they're all connected. But really what's going on is the bank is saying, until you get to the end of this year, we are not going to give you that money. And that makes it a discrete graph, made up of dots. So exponential functions are often discrete. In problem 4, interest is paid only once a year at the end of the year. So the graph consists of individual points that correspond to year 1, 2, 3, 4, etc. Not continuous, really shouldn't be connected up, but that's what we use. Both the table and the graph show that there's never exactly $1,500 in the account. You'll have to wait until year 9 and you'll actually have a little bit more money than $1,500. So it's the way they work. It's just how it is. Let's go down here. For ACEs, suppose you invest $500 in a savings account that pays 3.5% annual interest. When will the account contain at least $650? Sounds a lot like the one we just did. Do we have to use the fancy black formula, or can we use the short and red one? Yep, annual interest again. Oh, and here I am writing the longer formula down. Because I'm thinking to myself, I wish we had more examples here of the big black formula. All right, we want to know when this is at least 650. They started with 500. Help me out again. Interest rate is a decimal. 0.035. And we're again looking for t, but we can just make that an x in the graphing calculator. Too many zeros. All right, GC. Let's get this in here. We need 500, parentheses, 1.035, parentheses, to the x, and 650. What do you think? You think that's still going to happen within 10 years? Give it a try? Yeah, just use the window we had up there. Oh, except my y's were probably really huge, weren't they? Yeah, 2,000. We might be able to see it, but let me make that more reasonable. Yeah, it's within 10 years. So, Blinky, let us know. About 7.6 years, Blinky says. So we write 8 years. So we remember, yeah, you have to wait until the end of the year to get your money. Now, for B, it says use the table in problem 4 to determine when that account will contain at least $1,650. Oh, they want us to go back to the other one. Well, I already have this one in the calculator. Let's use this one. So, 1650. Table is second graph. And I just want to keep scrolling down until I see $1,650, which may take a while with this one. So right there, after 35 years, we'll finally be up over $1,650. So the book is just reminding us that we can use the table if we're not picky about dollars and cents, because the table, it only fits in so many decimals, and then it truncates it, it cuts it off, or it rounds in some cases. So we can use it. It's not going to be as accurate as if we actually put the numbers into the formulas. But it's there. It's something we can use. All right. We're done again. That was the last little formula right there. And like I said, I wish we had more that were practiced with the black formula, but we have plenty of them in the homework. So as you do the homework, you're going to be able to use those formulas. So here's day 3, and again, we're doing a few problems from the book, and then we're getting that 1 through 8, the rest of that compound interest worksheet done. So same as yesterday, I'll let everybody write that down. You don't need graph paper today. Yeah, I think I looked at them all and didn't see any graphs in there. I'll double check, but 23 to 25, 36, 37, and 42, and then the compound interest worksheet 1 through 8. Again, you might want to do the compound interest worksheet first while it's fresh in your mind. Got that formula, 2 formulas that you can use. Nope, no graphing. So no graph paper today.